Now we come to chapter 10. In chapter 10, we shall learn about Z transform. Z transform is simply a power series with coefficients, those are formed from some discrete sequence. Z transform is a powerful technique in solving difference equations. Application of Z transform are relatively new, and Z transform is used for discrete time signal and system. Chapter 10 is divided into two modules. In first module, we shall give an introduction to Z transform. First, we give the definition of Z transform. The Z transform of a sequence Fn, n ranging from minus infinity to plus infinity, is defined by Z of Fn, which is denoted by capital Fz, that is equal to summation n equal to minus infinity to plus infinity small f of n z to the power minus n as given by equation 1 for all complex numbers z for which the series converges. Here we make the following remark. Number 1, the series 1 converges at least in a ring of the form 0 less than equal to R1 less than mod z less than R2 less than infinity, where the radii R1 and R2 depend on the behavior of Fn at n equal to plus minus infinity. In fact, R1 is the limit n tend to infinity supremum of mod Fn to the power 1 by n, and R2 is limit n tend to infinity infimum of 1 by mod Fn to the power 1 by n as given in equation 2. Number 2 is the function capital Fz is analytic in this ring, but it may be possible to continue it analytically beyond the boundaries of this ring. Number 3, if Fn is 0 for n less than 0, then R2 is infinity, and if Fn equal to 0 for n greater than equal to 0, then R1 is 0. Number 4, let z equal to r e to the power I theta. Then Z transform evaluated at r equal to 1 is summation n equal to minus infinity to plus infinity f n e to the power minus I n theta, and this is the Fourier transform of the sequence f n from minus infinity to plus infinity. Now we consider some example. Example 1, let a be a complex number and let Fn equal to a to the power n for n greater than equal to 0 and 0 otherwise. Then the Z transform of Fn is summation n equal to 0 to infinity, because Fn is defined in that way, summation n equal to 0 to infinity a to the power n z to the power minus n, which is equal to summation from 0 to infinity a by z to the power n, and that is equal to 1 by 1 minus a by z for a by z mod less than 1. So, here capital Fz is the Z transform of small fn, and this is equal to z by z minus a for mod z greater than a. So, here we see that R1 equal to mod a and R2 is infinity. Next we come to example 2. Let a be a complex number and let Fn equal to n a to the power n for n greater than equal to 0 and 0 otherwise. Now the Z transform of Fn is capital Fz, which is equal to summation n equal to 0 to infinity n a to the power n z to the power minus n, and that is equal to summation 0 to infinity n into a by z whole to the power n. This is equal to a by z into summation n equal to 0 to infinity n into a by z to the power n minus 1, which we can write as a by z summation n equal to 1 to infinity n a by z whole to the power n minus 1, and if we substitute x equal to a by z, this can be written as x into d dx of summation n equal to 0 to infinity x to the power n, and this summation from n equal to 0 to infinity x to the power n is 1 by 1 minus x for mod x less than 1. So, that capital F z is equal to x d dx of 1 by 1 minus x, and that is equal to x by 1 minus x whole square, which is equal to a z by z minus a whole square for mod z greater than a. Here also R1 is mod a and R2 is infinity. Next we come to example 3. Let Fn equal to 1 for n greater than equal to 0 and 0 otherwise. So, Z transform of Fn denoted by capital Fz, this is equal to n equal to 0 to infinity z to the power minus n, and that is equal to 1 by 1 minus 1 by z, and that is equal to z by z minus 1 for mod z greater than 1. Here R1 is 1 and R2 is infinity. Next we come to example 4. Let Fn equal to delta n, and that is defined as 1 for n equal to 0 and 0 otherwise. So, Z transform of delta n, this is equal to 1 into z to the power 0, because all other terms are 0 in the series for Z transform, and only non-zero term is for n equal to 0, and Z transform of delta z gives as 1. Also, Z transform of delta n minus k, according to the definition, this is equal to 1 into z to the power minus k, that is equal to z to the power minus k for some fixed k, k may be 0, plus minus 1, plus minus 2, etc. Next we come to example 5. Let Fn equal to 1 by n factorial for n greater than equal to 0 and 0 otherwise. Then Z transform of Fn is Z transform of 1 by n factorial, and this is equal to summation n equal to 0 to infinity z to the power minus n by n factorial, and this is the series for e to the power 1 by z. So, Z transform of Fn is equal to e to the power 1 by z for all z. So, here R1 is 0 and R2 is infinity. So far we have learnt about Z transform, and we have found out Z transform of certain functions. Now we shall learn about the properties of Z transform. First property is linearity property. Let Z transform of Fn, which is denoted by capital Fz, and the region of convergence of Z transform of the sequence Fn be denoted by df, and similarly capital Gz is the Z transform of small gn, and the region of convergence of the Z transform of the sequence small gn be denoted by dg. Then Z transform of the function C1 small fn plus C2 small gn, this is equal to C1 capital Fz plus C2 capital Gz, Z belonging to df intersection dg as given by equation 3. Here C1 and C2 are constants, and the region df intersection dg contains the ring R1 less than mod z less than R2, where R1 is the maximum of R1f and R1g and R2 is the minimum of R2f and R2g. For proof, we write Z transform of the function C1fn plus C2gn. This is equal to C1 summation n equal to minus infinity to plus infinity fn z to the power minus n plus C2 summation n equal to minus infinity to plus infinity gn z to the power minus n, which is equal to C1 capital Fz plus C2 capital Gz defined in the domain described above. So, we have proved the linearity property. Next is shifting property, that is Z transform of the function f n minus k is equal to z to the power minus k capital Fz, where capital Fz is the Z transform of fn. For proof, we start with Z transform of f n minus k, and by definition this is equal to summation n equal to minus infinity to plus infinity f n minus k into z to the power minus n. If we substitute m as n minus k, then this becomes equal to summation m equal to minus infinity to plus infinity fm z to the power minus m plus k, and this is equal to z to the power minus k summation m equal to minus infinity to plus infinity fm z to the power minus m, and this summation is the Z transform of small fm, so that we can write it as z to the power minus k capital Fz. So, the shifting property is proved. Third property is that Z transform of a to the power n fn equal to capital F z by a, where a into R1f less than mod z less than a R2f, a positive. For proof, we start with Z transform of a to the power n fn, which is equal to summation n equal to minus infinity to plus infinity a to the power n fn z to the power minus n, which is equal to summation n equal to minus infinity to plus infinity fn into z by a whole to the power minus n, and which is equal to capital F of z by a. So, we have proved this property. Next, fourth property is Z transform of e to the power minus a n fn equal to f of e to the power a z. For proof, we start with Z transform of e to the power minus a n fn, which is equal to, according to definition, summation n equal to minus infinity to plus infinity e to the power minus a n fn z to the power minus n. This we can write as summation n equal to minus infinity to plus infinity fn e to the power a into z whole to the power minus n, and that is equal to f of e to the power z. Fifth property is to prove that Z transform of n fn is equal to minus z d dz of capital Fz, where capital Fz is the Z transform of small fn. For proof, we start with Z transform of n fn, which according to the definition is summation n equal to minus infinity to plus infinity n fn z to the power minus n. This is equal to z into summation n equal to minus infinity to plus infinity fn n into z to the power minus n minus 1. This we can write it as minus z d dz of summation n equal to minus infinity to plus infinity fn z to the power minus n, and that is equal to minus z d of capital F dz, because the summation is the z transform of small fn, which is denoted by capital Fz. Next comes the initial and final value theorems. First is the initial value theorem, which states that if fn equal to 0 for n less than 0, then limit mod z tend to infinity capital Fz is f0, small f0. For proof, we know since fn equal to 0 for n less than 0, so we can write its z transform as capital Fz equal to n equal to 0 to infinity fn z to the power minus n. So that if we make limit mod z tend to infinity, then the left hand side is limit mod z tend to infinity capital Fz. This is equal to, we separate out the term corresponding to n equal to 0, that is f0, plus limit z tend to infinity mod z tend to infinity summation n equal to 1 to infinity fn z to the power minus n. So, that is equal to f of 0 plus 0, because the summation is 0 as mod z tend to infinity. So, limit mod z tend to infinity capital Fz is equal to f0. So, this theorem is proved. Next is number B. If capital Fz is defined for r1 less than mod z, and for some integer m, limit mod z tend to infinity z to the power m capital Fz equal to a, then small fm equal to a and small fn equal to 0 for n less than m. For proof, we have z to the power m fz, this is equal to summation n equal to minus infinity to plus infinity fn z to the power m minus n. This is written according to the definition of Z transform. Now, we make mod Z tend to infinity. Left hand side as mod Z tend to infinity becomes equal to A because of this condition, and so A equal to limit mod Z tend to infinity summation n equal to minus infinity to plus infinity fn z to the power m minus n. Now, we break the summation into 3 parts, so that A is equal to limit mod z tend to infinity summation n equal to minus infinity to m minus 1 fn z to the power m minus n. Here n is less than m, plus fm plus summation n equal to m plus 1 to infinity fn z to the power minus n minus m. In the last summation, n is greater than m. So that we obtain A equal to fm plus summation n equal to minus infinity to m minus 1 fn z to the power m minus n, because this summation, this is equal to 0 as mod z tend to infinity, and here n is greater than m. Now, the series on the right hand side, that means this series diverges unless fn equal to 0 for n less than m. Thus, we get fm equal to capital A and fn equal to 0 for n less than m. So, we prove the second part of initial and final value theorem. Next property is that conjugate of Z transform of f minus n is equal to capital F bar 1 by Z bar. For proof, we start with capital F bar of 1 by Z bar, and this is equal to, according to definition of Z transform, summation n equal to minus infinity to plus infinity, small f n 1 by Z bar whole to the power minus n. Now, if we substitute minus n equal to m, then this becomes summation m equal to infinity to minus infinity to plus infinity, f bar minus m 1 by Z bar to the power m, and which we can write as summation n equal to minus infinity to plus infinity f bar minus n Z bar minus n, and this is equal to summation n equal to minus infinity to plus infinity f of minus n Z to the power minus n bar, and that is equal to, because the summation is Z transform of f minus n. So, this is equal to complex conjugate of Z transform of f minus n. So, we have proved this result. So, in module 1 of chapter 10, we have learned what is Z transform, and we have found out through some example Z transform of certain functions, and also we have learned some properties of Z transform. With this, we conclude module 1 of chapter 10.